This is part 3 of the chapter 2 lectures on fluid statics, and in this case we're going to look at forces on submerged surfaces that are curved. So in part 2 we looked at surfaces that were flat. Now we're going to look at some curved surfaces like this corner right here. It's a tank like a tank in the previous problem, but now it has a curve on the surface down below in the corner. So the trick to doing this type of a surface is to draw yourself a little squared off corner right here. Bring that over here. So these are the lines that I just drew in the tank diagram. So now I have this pie-shaped chunk of water. It goes back into the corner here, or back across the tank. So remember, it's 3 meters wide. So it's kind of like a quarter of a cylinder. So once we've drawn that, we can just do the free body diagram on that chunk of fluid in the corner. And so we have a force on top. That's really the force that has to do with the column of water above it. And then we have the force on the side we'll call F2. And that's the force of the water coming in from the side. And then we have the weight of the water itself in that quarter cylinder. We want to know the magnitude and the direction, I should say, of the forces on that corner. So if we first figure out the magnitude of these three forces, the first one, the magnitude, is simply from the volume of the water there above the flat surface. So that's y1, the depth to the top of the flat surface, times the area, which is 1 meter times 3 meters. And then rho g is the density and gravity. So that gives us about 147 kilonewtons going down on the top of that flat surface. F2, remember we take the centroid of the flat surface that we're working on there, the vertical flat surface. So that's halfway down the side of our flat rectangle. And so that's at a depth of 5.5 meters. And again, we're going times the area, which is 1 times 3. So we get about 161 kilonewtons, or 162 kilonewtons. And then the weight of the water is just the volume of the corner times rho g. And so the volume there is 3/4 times pi, which is the volume of 1/4 of that cylinder. So that's not as much, it's about 23 kilonewtons. And that makes sense because that's just a small chunk of water compared to the pressure on the side and the weight of all that water above it. So where are these forces applied? So the application of the force on top is right in the centroid of that face AB. So if we look back up here, it's right in the face of this top corner, right in the center here, as we've drawn it pretty much. Now the F2 is very much like the gate problem that we did in the previous part. And that one we know is going to be applied just below the center because there's going to be more pressure down here and less pressure up here. So remember, we figure that out using the parallel axis theorem, where we take the depth to the centroid and we add on this calculation from the second moment of inertia, which for a rectangular wall, and that's what the face of this quarter cylinder looks like, is a rectangle. And we plug in the geometry here, and we find out that it's just a little bit below the centroid of the surface AC, or about 0.14 meters below that centroid. So the weight is going to be applied through the centroid straight down. We know that. The force is in the middle. Force 1 is in the middle, right here. Weight here through the centroid of the shape. And F2 we just figured out is going to be just a little bit below the center, 0.64 down from the surface, from the AB surface. So that's where our vectors are being applied. To find out the resultant force, we sum the verticals and sum the horizontals. The vertical is the top weight of the water in the corner. The horizontal one is the pressure on the side. So we have two forces there, horizontal and vertical. We add those and we get the resultant force of about 235 kilonewtons. We can take the ratio of the vertical force to the horizontal force, take the inverse tangent of that, and we'll get the angle with the vertical with respect to the, angle with respect to the horizontal dimension, and that's about 46 degrees. So that's pretty much all we needed to know. Now, if we wanted to know exactly where it was applied, we know we could do it. It'd be a little bit rough, but we would have to pick a location and take the moments, sum the moments around a moment pivot point like C. We know this corner's not moving, so we would sum the moment arms, try to pick a convenient place. If we pick C, we know F1, we know the moment arm here is 1 minus 0.64. We know this one is 0.5 because it's 0.5 over from here. And then we could figure out the moment, or the distance of the moment arm XR for P, because we know P would be acting perpendicular to this corner. So I'll leave that to you. You can work it all out, and you will find that let's see, it comes out to be located at this point. See if you can find that or work through these numbers. But really, the most important part of this was right up to here. And then we weren't really asked for the rest of it, but we just did it for the fun of it. And hopefully you'll remember that from your statics. But mainly, I wanted you to get up to this point where you could get the angle and get the three forces and turn them into one resultant force. So this is the main trick for these types of problems. Find yourself a convenient way to square off the corners, and then you can work on flat surface problems and just figure out the weight of the weird shaped part of the problem. Those are the main issues. So hopefully you got that. Maybe watch it again, and if not, come and see me for office hours.